Welcome back to the highlights from the past 25-minute symposium. I am joined here today by Drs. Farnas Khosravi, Dr. Benedikt Geyer, and Lucas Dreyer, who is not a doctor yet, but soon. They have arranged a mini symposium on dynamic, adaptive, scalable methods in Earth systems modeling. This sounds very advanced, Dr. Khosravi. Tell me more about it. Why did you do this?
Why do we do it? Because we think adaptive grids are a good technique for the future. So we can make Earth system modeling more efficient, faster. So we think it has a lot of advantages. And we did this mini symposium because we are a group working currently together in a project and wanted to show, because we are now almost at the end of our project, we wanted to show our results to the community, to engage with the community and to get some feedback and look how the interest is. And we saw that the interest was quite huge, we could say. So
the dynamic aspect here is that you're changing the resolution or the architecture of these grids as you go.
Exactly. But the typical standard is we have a Cartesian grid for atmospheric modeling, and then we do the refinement of this grid at areas where it's necessary and where it's where we have fine-scale structures, and we remove some grid points or cells in the areas where there's nothing interesting happening. And then we can, with that adaptation, we can really be very efficient because we have the high resolution only at that places where we really need it.
So that sounds important. What did you learn?
We learned that dynamic adaptive mesh refinement is a really great tool to reduce runtime and reduce the memory footprint, and therefore also reduce the energy usage of simulations. One of the examples had one-time reduction of more than a factor of 10, while still maintaining the same error. So adaptive mesh refinement is really useful to increase your error, maybe even if you can go to a finer level with the same runtime on your supercomputers. But we also found out that in Earth system modeling, you have a lot of challenges that are specific to that area. So anisotropic refinement was a huge thing that we didn't look at before, which we need to consider more during simulations. Or specific phenomena for the discontinuous Galerkin solver, which Benedikt investigated a lot.
So this sounds really cool. The stuff, the intersection, at least I love with Pascal. One part hardware, hardcore energy, all the way to the applications, but then also the numerical algorithms in the same symposium. That sounds really cool. So what will this help you with in the future? What's the next step?
Well, that's of course the most important question, I think. So as Farah said, there was a lot of interest, and I think also from the practitioners we received a lot of interesting questions, and they of course would like to know if this will in the end bring some benefits for their daily life. And that has to be discovered, I think. So far we were looking at synthetic test cases, and now I think we really have to move to the realistic cases. Yep. We have nice algorithms, we have now a nice machine in Jülich, and now we have to use it.
That's an amazing resource, right? Largest computer in Europe. Is there anything holding you back? Or do you have infinite resources now?
Not exactly. We are quite fortunate to have this supercomputer, which is going to start soon, to be ready for our own simulation and operation, exactly. But what always is lacking is, of course, manpower and funding.
So we need to make sure to fund the scientists too. That's an important end message. Thank you so much for joining us.
Yeah, thank you too.
Thank you.
Thank you.